For this lesson, we're going to be continuing our look at derivatives. So these are the extensions of our original work on limits, and these provide a much more condensed set of rules for us to be able to look at things like rate of change and the slope of the tangent and some other properties that we're going to be interested in. So today we're going to be looking at the product rule. And the product rule is defined as we have a product of two or more functions. So we're going to start off with two functions. So if h of x is defined as the product between f of x and g of x, in other words, f of x multiplied by g of x, then the product rule itself says that the derivative of h of x, h prime of x, is, and the way I learned it myself and the way I phrase it in my head whenever I think about this, it's the derivative of the first times the second plus the first times the derivative of the second. So you can see the derivative of the first and then a multiply by the second unchanged, and then I add to that the first function unchanged multiplied by the derivative of the second. You can refer to your textbook. I'm not going to use this note or this time to derive this one, but you might want to take a look at that proof from what we call first principles, which means we start with the limit definition that we've been working with, and so you can refer to that on page 86 of your textbook. Another example, you really need to just start with this, but another example that's worth exploring, or at least thinking about, is this one. If y is made up of the product of three functions, then the derivative of this is going to be the derivative of the first multiplied by, you can see the next two functions are unchanged, and then the first times the derivative of the second, and the third is unchanged, and then the first and the second are unchanged multiplied by the derivative of the third. So it can be extended from there. We could come up with this expression using the basic expression for the product rule. And that's something you could be asked to do on an evaluation. So not just memorizing it, but could you actually prove using this definition, could you extend it to this new definition? So that's something for you to think about, or you may even come across something like that in your homework, in your assigned work. So let's go ahead and apply this right away. And so I've got two examples here, and I've been asked to take the derivative of each, and I'm going to do that using the product rule. And maybe I'll just remind you up here. So if h of x, actually I'll just go ahead and write it as h prime of x. So that's the derivative of the first times the second plus the first times the derivative of the second. And so I'm going to now try to apply that to my first example here, which is I've got 2x plus 4 multiplied by 3x minus 5. Now we could expand this just to binomial terms, expand that, we would end up with a quadratic, and then we would be able to apply the power rule, which is what we did in a previous lesson. But the idea here is we want to go to our derivative in the first step. We want to go directly to the derivative. So the way that works, now I'm going to write it out exactly the same way that we have here, and if it helps you to, sometimes it might help you to label these. So I'm going to call that one f of x and call that one g of x, for example. And so it's the derivative of the first times the second plus the first times the derivative of the second. Now I wouldn't actually want you to always write that out, but as you're starting to do this, that might be a good idea just to get your head wrapped around it. So let's go back up here, take a look at f of x. What's the derivative of 2x plus 4? Well, the x term, that's to the power 1, so that just becomes the value 2, and the derivative of the constant 4 is 0, so this is just 2, times the second, which is 3x minus 5, plus the first, which is 2x plus 4, times the derivative of the second, which is simply equal to 3 using the power rule. And now I'm going to expand and simplify this, so I end up with 6x minus 10 plus 2x times 3 is plus another 6x, and plus 4 times 3 is plus 12, and I end up with 6x plus 6x is equal to 12x, negative 10 plus 12 is plus 2. So there is my final answer. 12x plus 2 is the derivative. Let's now take a look at b. So b is already written here. I'm just going to work from there. So now, and once again, it wouldn't be the worst idea. The only thing is we've already got f of x defined here, so we might define this as g of x, and we might define this as h of x. So f prime of x is going to be the derivative of the first times the second plus the first times the derivative of the second. And now let's go ahead and start to fill that in. Slightly more complicated, but not terribly so. It's just we have to do this derivative. We'd like to be able to do this derivative in one step. Just be careful with it. So the derivative of 3x squared is 6x. The derivative of 4x is 4. And the derivative of negative 6 is 0 because it's a constant. So that's the derivative of the first times the second. 2x squared minus 3x minus 9 plus the first unchanged 3x squared plus 4x minus 6 times the derivative of the second, which is 4x minus 3. Now unfortunately we still have quite a bit of work to do here, which is we really should expand and simplify this. And it's straightforward. It's just really just bookkeeping. It's just making sure that we don't make any silly mistakes. So being very careful one at a time, I'm going to take this first term, 6x times 2x squared. That's equal to 12x cubed. And then I get 6x times negative 3x is minus 18x squared. And 6x times negative 9 is going to be minus 54x. And then 4 times 2x squared is plus 8x squared. 4 times negative 3x is minus 12x. 4 times negative 9 is minus 36. Now I have to take care of this one. I'm going to have to move on to the next line to do this next one. So now I've got a positive in front times 3x squared times 4x. So that's going to be plus 12x cubed. And then I've got a positive in front times 4x times 4x again. So that's going to be plus 16x squared. And then I've got a positive negative 6 times 4x. That's minus 24x. And now I have to do positive 3x squared times negative 3. That's minus 9x squared. Positive 4x times negative 3 is minus 12x. And negative 6 times negative 3 with a positive in front is going to be positive 18. And now we have to gather together like terms. I look at my x cubes and I see I have 24x cubed. I take a look at x squared. I have negative 18 plus 8, so that's going to be minus 10x squared, plus 16x squared. So I said that was negative 10 plus 16, so now I'm at positive 6x squared, minus 9x squared, so positive 6 minus 9, so I end up with minus 3x squared. Negative 54x minus 12x is going to be negative 66x, minus another 24x, so that's going to be negative 70, negative 90x, and minus another 12, so that's minus 102x. And finally, we have our constants. Negative 36 plus 18 is minus 18. Now, it wouldn't be the worst idea in the world for me to just double check this here. So 12x cubed plus 12x cubed is equal to 24x cubed. So I've taken care of those. Actually, maybe I don't want to cross them out. That's kind of poor form, but I'm going to say, okay, I've taken care of those. Minus 18x squared plus 8x is minus 10x. Minus 10x plus 16x squared is plus 6x, so that's taken care of, that's taken care of. Plus 6x squared minus 9x is minus 3x squared, which I have here. Negative 54x minus 12x is negative 66x. minus 24x, that gets me to minus 90x, minus another 12x is minus 102x, and then my constants, negative 36 plus 18 is equal to minus 18. So that looks good. Next example, find the points on the curve which satisfy the equation of the curve is f of x equals 2 times x minus 1 times 5 minus x, and the absolute value of the slope of the tangent line is equal to 4. So let's get an idea, first of all, when we look at this curve. A quick sketch of the graph. I know I've got a 0 at 1, and it looks like I've got a 0 at 5. Now you have to be careful. Your first instinct here might be that you've got a leading coefficient that's positive, so this opens up. But if we take a look, it's the leading coefficient on the x squared term, and this is actually going to be 2 times x times negative x, so that's negative 2x squared. This actually opens down. So it's going to be something like that, just a rough sketch. So what we want is the absolute value of the tangent to be equal to 4. Well, what does that mean? If the absolute value of the tangent is equal to 4, that may mean that the slope of the tangent is equal to 4, or that could also mean the slope of the tangent is equal to negative 4, because the absolute value of negative 4 is equal to positive 4. So we're looking for where is this fairly steep slope. So we're looking for where on here do we have a slope of positive 4, and where along here do we have a slope of negative 4. So we're wondering, where are these points? Now, I've kind of, the way I've drawn that, put those question marks in, because this is a parabola and because these two slopes are symmetric, I actually expect these 2 points to be at the same level. But the point, what I'm trying to say here is, I don't know really from this very rough sketch, I don't know where these slopes of positive and negative 4 actually occur. Slope of negative 4 there, a slope of positive 4 there. So the way that I do that is I remember the relationship is that the slope of the tangent is equal to the derivative of the function. So I'm going to go ahead and take the derivative of the function first of all. So f prime of x is equal to, now I've got a constant in front, and so that constant can just stay there. And then I can apply my product rule. So it's going to be the derivative of the first. So the derivative of the first is simply equal to 1 times the second, which is 5 minus x, plus the first, which is x minus 1, times the derivative of the second, which is equal to, now the derivative of this 5 is equal to 0, and then the derivative of negative x is equal to negative 1. So that becomes 2, and now I just go ahead and multiply that out. That's 5 minus x, and this one becomes positive x times negative 1 is minus x, and then positive times a negative is positive 1. And let's take an extra line to do this. So I end up with negative 2x, and then 5 plus 1 is equal to 6. And so overall, I end up with negative 4x plus 12. And that is my f prime of x. But that's also the slope of the tangent line. So what we want to do is we want to solve, we have two things we want to solve. We want to solve the slope of the tangent equals 4. So that means 4 is equal to negative 4x plus 12. Subtract 12 from both sides, I end up with negative 8 equals negative 4x. X is equal to 2. And I also want to solve slope of the tangent is equal to negative 4. And so I get negative 4 equals negative 4x plus 12. Negative 16 is equal to negative 4x. X is equal to positive 4. And I just want to take a look at how the question was worded. Find the points on the curve which satisfy this. So I have only found the x coordinates, And so now I need to also find the points. I need to go back and I need to sub in f of 2 because x is equal to 2. And my original expression, just to remind us, 2 times x minus 1 times 5 minus x. So this is going to be 2 times, but instead of x minus 1, it's going to be 2 minus 1, and it's going to be 5 minus x. And so we end up with 2 times 1 times 3 is equal to 6 for that one. And then we have to also figure out what is f of 4. F of 4 is equal to 2 times 4 minus 1 and 5 minus 4 in this case. And we end up with 2 times 3 times 1, which is equal to 6. And as I predicted, when I talked about it up here, I said I expect these two values to be symmetric, to be the same y values. And sure enough, we did end up with the same y values. So therefore, the absolute value of m tangent is equal to 4 at, and what are my 2 points? One of those points is 2, 6, and the other one of those points is 4, 6. And from this symmetry, we can actually tell that the vertex is halfway between. The vertex should be at 3. And if we had talked about it, well, halfway between 1 and 5 is also 3. So there's our vertex. So there's a lot we could have deduced from this beforehand. But it's nice to see that in our final answer, what we should have anticipated is actually being borne out. And as you can see, I've produced a slightly nicer version of the graph here. So there are the zeros at 1 and 5, and here are the 2 points where the tangent lines, one of those tangent lines is equal to positive 4, the tangent lines, the slopes of the tangent lines are positive 4 and negative 4. Okay, that's it. Fairly short lesson. Really, it's just that new rule and then trying to put that into practice.